classes for JEE and NEET. We are in the chapter alkanes and we are learning about conformational isomers of N-butane. Already we have studied about conformational isomers of ethane. In this session we will discuss about the conformational isomers of N-butane. What is N-butane? Right? N-butane, generally called a normal butane also. Right? So bute means anyway 4 carbon atoms. If all the 4 carbon atoms are in a straight chain, CH3, CH2, CH2, CH3. If they are in the straight chain without any branching, that is called as a N-butane. Right? It can also be considered as a dimethyl derivative of ethane. See, there is a ethane. Okay. CH, H, H. What is this? Ethane. C2H6. C2H6 is ethane. This is ethane. So two hydrogens. See here, this hydrogen and this hydrogen are substituted with the methyl groups. Then what do we get? N-butane. So dimethyl derivative of ethane in which one hydrogen atom of each carbon atom is replaced by methyl groups, then that is called as a N-butane. So let us write the numbers for these carbon atoms: 1, 2, 3, 4. Okay. Already we have studied that if there is only single bond between carbon and carbon, the molecule can be rotated along that sigma bond and the different conformations are produced. Let us consider here the rotation along the carbon 2 and 3. Let's consider rotation, free rotation of the molecule, rotation of molecule along second and third carbon atom. So along second and third carbon atom, the molecule is rotated and different conformational isomers are studied here. There are infinite number of conformational isomers already we have studied, but among them we will study a few number of conformational isomers. In this session, we are speaking the conformational isomers produced when the rotation is done along the second and third carbon atom. Already said. The different conformational isomers produced are, right? So let us see here, this is carbon number 1, this dot is carbon number 2, this circle is carbon number 3, and this is carbon number 4. Carbon number 4. So we are rotating along second and third carbon atom, right? So what is this conformation called as? See here, two methyl groups are at 180 degrees. Dihedral angle here between CH3 and CH3 we are considering. CH3 and CH3 we are considering. Here theta is equal to 180. 180. So these two are bulky groups than hydrogen. Bulky means more size. See C, H, H, H. The size of CH3 is greater than hydrogen, right? So this is having larger size. So we are speaking with respect to these methyl groups. When we are speaking with respect to methyl groups, here if you see, these two methyl groups are at 180 degrees. The dihedral angle is 180 degrees. And such conformation is called as what? Staggered conformation, which is also called as anti-conformation. And as these two methyl groups are at 180 degrees, they are oriented with maximum angle between them. There will be very much repulsive forces. As there is very much repulsive forces, it is the most stable conformational isomer of N-butane. So we can say that it is highly stable. Now what you are doing? You are rotating this molecule through 60 degrees. What you are doing? On rotating this molecule through 60 degrees, what happens here? This is the first carbon atom. This is second carbon atom. This circle is third carbon atom. Here is the fourth carbon atom. Now CH3 and H got eclipsed. The CH3 and H eclipsed, H and H eclipsed. Eclipsed already we have studied that. The front atoms or groups are eclipsing the back one. The back atoms or groups are eclipsed by the front one. The back the rare carbon groups, the rare groups or atoms are exactly behind the front atoms or groups. Then such conformation is called as what? Eclipsed conformation. Here CH3 is eclipsing hydrogen, H is eclipsing CH3. So in that way, eclipsed conformation. This is eclipsed conformation. So on rotating the staggered by 60 degrees, we get eclipsed conformation. Again, let us rotate this by 60 degrees again. So 1, this dot is 2, this circle is 3, and this is 4. So here, what is the angle between the CH3 and CH3? This theta is how much? 60 degrees. So such conformation, when CH3 and CH3, this angle theta is equal to 60, and that is called as gauge conformation. Is that a gauge conformation? Again, if you rotate it through 60 degrees again, if you rotate it through 60 degrees, not this one, fifth one, let us see. If you rotate it through 60 degrees, so this is third one, so this is fourth one. See, first carbon, this is second carbon, third one, and this is fourth one. First carbon and fourth carbon, that is two methyl groups are eclipsing with each other. So they are in eclipsed form. The theta is equal to how much? 0 degrees. So between CH3 and CH3, what is the angle? 0 degrees. Such eclipsed form. Here in the second conformation, if you are seeing, CH3 and H are eclipsed. Okay. Angle between CH3 and H, here angle between CH3 and H is 0 in the second conformation. But here in the fourth conformation, if you see, both CH3 groups are having a dihedral angle of 0 degrees. Such conformation is called as fully eclipsed or total eclipsed form. Total eclipsed. Again, when you are rotating one of the, see what you are finding, we are keeping the second carbon atom rigid, it is not moving. Without moving the second carbon atom, we are rotating the third carbon atom. 60 degrees rotation means what we are rotating? We are rotating the third carbon atom. And rotating the third carbon atom, all these different conformations we are finding. Again we are rotating the third carbon atom to 60 degrees. Again here the angle, what angle you are finding? Angle is equal to 60 degrees, dihedral angle. Again similar type, see, third conformation and fifth conformation are almost same, are same. That is the reason why they are called as again gauge conformations. And rotating the third carbon atom again to 60 degrees, then what do you get? Eclipsed conformation. Here you have to see that two types of eclipsed are there. One is eclipsed, another is total eclipsed or fully eclipsed. In fully eclipsed, you find dihedral angle between CH3 and CH3 is equal to 0. Okay. So let us see this eclipsed second conformation. Which conformation? Second conformation. In the second conformation, what you are finding? We are finding CH3 and H. This H. This is what? H. H and CH. See here, energies are given when CH and CH, when CH and CH are eclipsed, then the molecule will have repulsive force. Due to that repulsive force, how much energy it increases? 4.2 kilojoule per mole. Here, what are eclipsed? CH and CH, this one. What is this? CH, CH. So that 4.2 kilojoule per mole. CH, here, this is what? CCH3, this is CH. Okay. Then how much energy is increased due to this? How much energy is increased due to this? Here it is 4.2 kilojoule per mole. Here CH and CH3, this is 5.6 kilojoule per mole. Here also 5.6 kilojoule per mole. Overall, increase in the energy of the molecule 5.6 plus 5.6 plus 4.2, 12, 14, right? 15.4 kilojoule per mole. So what is this energy? This energy is possessed by this eclipsed form. This eclipsed form is having 15.4 kilojoule per mole greater than the staggered form. Greater than the staggered form. So we are here, staggered or anti, this is most stable one. Its energy is not equal to 0. We cannot consider this energy possessed by staggered form is 0. It will possess some energy. When compared with the staggered, how much energy, more energy eclipsed is possessing? Eclipsed is possessing 15.4 kilojoule per mole greater than that of staggered form. Okay. So next consider coming to gauge form. So gauge, if you see here, you can see CCH3, CCH3 when they are at 60 degrees, then how much energy is increased due to repulsive forces? How much? 3.8 kilojoule per mole. So let us draw this gauge form. CH3, this is CH3, H, H, H and H. So they are at how much? 60 degrees. Theta is equal to 60. Then the increase in the energy is 3.8 kilojoule per mole. So Gauch conformation is having 3.8 kilojoule per mole energy greater than that of staggered form. Greater than that of staggered form. Okay. Next, let us go with fully eclipsed form. Fully eclipsed. In fully eclipsed, this is CH3, CH3, H, 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 and this is fully eclipsed conformation. CCH3, CCH3 with theta is equal to 0, then the energy increased will be 13 kilojoule per mole. How much energy is increased here? 13 kilojoule per mole. Here 4.2 kilojoule per mole. Here how much? 4.2 kilojoule per mole. So total increase in the energy when compared with staggered form for fully eclipsed form is 13, 4.2, 4.2. How much? 4, 1, 21.4 kilojoule per approximate. So here, what is this fully eclipsed form or total eclipsed form? See, this total eclipsed form is having energy, how much? 21.4 kilojoule per mole, greater than that of fully eclipsed staggered one. Greater than that of staggered or anti. Right? So now let us go with the energy. So these are the conformations of what? N-butane, different conformations of N-butane. So we have how many types of conformations? One is staggered or anti, which is highly stable one, and we have fully eclipsed, which is least stable conformation, and another two conformations, one is eclipsed and another is Gauch. So there are 4 different types of conformations, right? So let us discuss about the relative stabilities of conformations of N-butane. So the highly stable one is staggered. Staggered, or which is also called as anti. It is having least energy. Least energy, maximum stable. It is having maximum stability. When compared with this anti, total eclipsed is having 21.4 kilojoule per mole approximately. Eclipsed is having 15 kilojoule per mole approximately, and Gauch is having 3.8 kilojoule per mole energy when compared with the staggered. When compared with staggered, Gauch is having more 3.8 kilojoule per mole, eclipsed is having nearly 15 kilojoule per mole, and total eclipsed is having 21.4 kilojoule per mole. Right? So this stability is important. Based on the stability, we are asked questions in competitive examinations. So let us see this diagram, potential energy diagram. Here this is 0 degrees. We are rotating it through an angle of 60. When it is rotated through an angle of 120, this is 180 rotation. This is 240, this is 300, this is complete rotation 360 degrees. Okay, so now let us take it is 0 degrees, that is dihedral angle is 0. When dihedral angle is 0, it is in totally eclipsed form. Its energy is how much greater than that of how much energy greater than that of staggered? How much energy greater than that of staggered? 21 kilojoules. This energy difference between staggered and total eclipsed is how much? 21. 21. This is the angle. This is not the energy here. This is 0 degrees, 60 degrees, 80 degrees. That's it. So between staggered and total eclipse, the energy difference is 20. Between gauge and staggered, it is 3.8. Between staggered and eclipsed, the energy difference is 15 kilojoule per mole. Understood? Okay. So when it is 0, when dihedral angle is 0, it will be in total eclipsed form. If you rotate it through 60 degrees, it will get gauge form. Again, if you rotate it through 60 degrees, we get what? Eclipsed form. Again, if you rotate it through 180 degrees, we get staggered form. If you rotate it through again 60 degrees, we get eclipsed form. Again, if you rotate it through 60 degrees, we get gauge form. Again, if you rotate it through 60 degrees, we get total eclipsed form. So in this way, their energies changes due to those torsional strain and steric strain. So due to repulsive forces, their energies increases, and these energy barriers are very less. So the molecule continuously undergoes rotation from one conformation into another conformation. So this order of stabilities is very important. We need to remember this based on the energies. Based on the energies, we have derived this order. Okay. That is about the conformational isomerism of N-butane. Let us see, in some of the molecules, now up to now we have seen that the staggered one or anti-conformation is the most stable one, but in some of the molecules, than anti, which conformation is more stable? Gauge will be more stable. Which will be more stable? Gauge will be more stable. So in some molecules, gauge is more stable than anti due to intramolecular hydrogen bonding. So there is intramolecular hydrogen bonding. So due to this intramolecular hydrogen bonding, what happens? Stability increases. What is that? The stability of the molecule increases. See here, you are finding ethylene glycol. What is that? Ethylene glycol, or we can say this is 1,2 ethane 1,2 diol is IUPAC name. Okay, ethylene glycol is common name. If you look into this gauge representation, see gauge representation or gauge conformation, there is theta is equal to 60 degrees. Here it is satisfying all the conditions of hydrogen bonding. So the hydrogen bonding occurs between hydrogen of one OH and oxygen of another OH. When does this hydrogen bonding is occurring? When it is in 60 degrees. And this hydrogen bonding is happening in the same molecule. So this is called as what? Intramolecular hydrogen bonding. Intramolecular hydrogen bonding. So this is gauge representation. But than anti, see in anti, two OH are at farther at an angle of how much? Theta is equal to 180 degrees. But still, though they are at an angle of 180 degrees, they are farther apart, their repulsive forces are less, but still gauge form is more stable than anti form, because in gauge form there is intramolecular hydrogen bonding. So in some of the molecules like ethylene glycol, gauge representation or gauge conformation is more stable than anti conformation. And in not only that, in another molecule also generally asked 2-fluoroethanol. So 1, 2, right? So 2-fluoroethanol. 2-fluoroethanol is IUPAC name. In this again, when it is in the Gauch form, it is satisfying all the conditions of hydrogen bonding. So hydrogen bonding is formed, and this hydrogen bonding is formed between hydrogen of OH and fluorine of fluorine attached to another carbon atom, and this is happening only when the angle is how much? 60 degrees. Theta is equal to 60. In Gauch form, this intramolecular hydrogen bonding is happening. Right? So Gauch form is more stable than anti. Why? Though in anti OH and F are at farther distance, Gauch form is more stable than anti due to this intramolecular hydrogen bonding. Stability is increasing due to intramolecular hydrogen bonding. This intramolecular hydrogen bonding is an attractive force. Due to that attractive force, this molecule will be present in that form for more time, so it will be more stable form. You may be having doubt that sir, when these two are at theta is equal to 0, is there no intramolecular hydrogen bonding possible? No, intramolecular hydrogen bonding is not possible if theta is equal to 0. Right? So we have to remember these two examples. Generally asked these two examples in the examination. What are those two examples? One is 2-fluoroethanol and another is ethylene glycol, in which anti is not more stable than Gauch, but Gauch is more stable than anti. Right? Hope so you understood very well. We shall meet